Okay, so it's 12:05. Let's get started. So today we're going to talk about the Max-Flow Min-Cut Theorem. And yesterday I mentioned that this week's what we're focusing on is, well, the basic philosophy is either you can have a high flow in a network, or if you can't find a large flow, then the only reason is that there's some sort of small bottleneck which prevents it, right? And that sort of theme came up yesterday in Menger's theorem, and this in the Max-Flow Min-Cut theorem, this is even more kind of, well, prominent. Okay, so here's the setup. So let D. So again, we're going to look at digraphs, but okay, technically, I want to look at multi-digraphs. So I'll explain what that is. So let this be a multi-digraph. So it's the same thing as a digraph, except so it's just a digraph, a directed graph, except A is a multiset, which is the same as a set, except it allows multiple copies of the same arc. So you can have, so for example, in a digraph, in a digraph between any two vertices, so in a digraph, the arc UV, occurs or appears, at most once. That means almost one time in the digraph, but in a multi-digraph, U and V might be joined by lots of arcs. So it's just it actually doesn't turn out to really matter too much for this problem, but it's convenient to think about. So it's kind of like you have two cities in this network or something. There could be three completely different roads to go between them, right? Which don't go to any other cities. Okay, so this is just the beginning of the setup. So D is a digraph, and now we have a capacity. So S. So throughout this lecture, S and T are just going to be vertices of the digraph. Again, S not equal to T, and we're going to fix a capacity function C, which maps each arc to a positive real number. Or, yeah, actually, maybe I'll make it strictly positive real numbers. So basically, you have these arcs in the digraph. Each of them has a certain capacity. Okay? You can think of this like, so if you think of your digraph as being a system of roads or something, then maybe the capacity is like the maximum possible cars that can travel along this road in 1 hour or something. Like, some sort of, or if it's a system of pipes, it's like the maximum amount of water or oil or whatever you can push through that pipe in an hour, right? It's the total, the capacity, the maximum possible. And so our goal today, so I'll just state this informally and then I'll make it clear exactly what I mean. But our goal is to find the maximum flow. Okay, I'm putting it in quotations for now, but I'll tell you what a flow is in a second. So in the digraph D, subject to the capacity function. One thing I didn't say, I should say, so flow, when I say flow, we have these special vertices S and T. So in particular, we're going to look at a flow from S to T. So you can think of S as being sort of some sort of source. So that's kind of, I don't know, if you think of a transportation network, you can think of, I don't know, this is where all the cars are coming from, and then T is where they're going to, and you want to push as many cars through the network as you can. Or if you think of, some sort of water pipes, or oil or something, S is where the oil starts, T is where you need to get it to, and you want to push as much through the system as you can, but you're restricted by the capacity function. So you can't push arbitrarily amount through. You can only do what the capacity function will let you do. Does that Is it clear that, I mean, vaguely what we're trying to do today? Okay, so let me now define exactly what a flow is. So a flow from S to T is a function f from the arcs to, so this time, non-negative real numbers. So we allow 0 such that, you should think of the flow as kind of the amount of stuff which is going through that arc at any given time. And so remember, we need to, so we're going to have two conditions. So, yeah, perhaps, so apologies for this. So I'm going to write here. Sorry, I keep on forgetting to write things. But so I want to flow from S to T subject to C, right? So it's subject to the capacity function. So it's a function f from the arcs to non-negative reals such that, so we need the flow on a given arc to be at most the capacity. Okay, and we need another condition, right? Because, so if you think of this as a sort of network problem, right? You're flowing through a network. If you think of cars or something, right? So if you have some sort of road, some one-way streets like this, and you know, for example, 5 cars come down this road every hour, and 2 cars come down this road every hour. Well, you know, how many are going to come down this road? Well, basically, I mean, they have to merge there, and we're assuming nobody kind of stops there and you know, goes off the road, right? So definitely 7 has to come down this road every hour, because the flow in has to be the flow out. So that's the condition we need for every vertex except for the special vertices S and T. So for all vertices in the vertex set except for S and T, we have this condition that the sum over arcs A going into V of f of A has to equal the sum over all arcs A going out of V. So this is probably not the most elegant notation here, but hopefully it's clear what I mean of f of A. Okay. KV. What? Yeah. So you can write this as summing over all all vertices. Let's say K, or let's say U or something, right? So it's summing over U U comma A or V, f of UV equals sum over all, let's say W V, f of VW, right? But anyway, in either way, yeah. But hopefully this is clear. Sometimes, I mean, I don't know if any of you've done any physics, like to do with circuits and things like that, right? But this is sometimes called Kirchhoff's, or Kirchhoff, I'm not sure how to pronounce it, but condition. Okay, it's not important for you to know that, but if you've seen any kind of electrical circuits, electrical networks, this will be hopefully clear. Okay, so here's just an example that I've drawn. So so on each edge, or in each arc, the red number is the capacity. I know that red is not the most visible. I tried to make the numbers big. So, you have capacity 5 here, 4, and so on. And the yellow is the flow. And if you check any vertex, for example, this one, you see that the flow coming in is 2, the flow coming out is 2, except for these special vertices S and T, where the flow is originating at S and ending at T, right? So there you don't need to have Kirchhoff's condition, but everywhere else you have to have it. Okay. So is it clear what a flow is? Okay. So now, so the value of a flow is basically how much stuff you're managing to push through the network. Okay, so the value, definition, the value of the flow F, which we'll just write as, I'll just simply write value F to denote the value. Well, how much stuff are you managing to push through the network? Well, if you think about it, you can think of it as how much stuff is coming out of the source, or how much stuff is going into the sink. Or sorry, the sink meaning, the source is S, sometimes I'll call T a sink because all the stuff kind of sinks into T. So it's the sum over all arcs coming out of S, arcs A coming out of S, f of A, or equivalently, so it's not hard to see, although I perhaps won't prove it, but because you have this Kirchhoff's law, or Kirchhoff's condition, this is equivalent to saying the sum over all arcs A into T of f of A. So this is just, the number, if you think of these as cars or something, it's the number of cars which leave the source, but it's the same as how many come into the sink in each hour or whatever. Okay? And naturally, we're interested in maximizing the value of a flow. That's what we're really after. Ooh, dear. Okay, this is interesting. I have no idea. Aha, good. You just press buttons randomly long enough, it's going to work. Okay. Good. Okay, so we want to maximize flows. Now, again, everything comes down to figuring out if you have some bottleneck which is going to stop your flow. So, okay, let me say. So this is another key definition. So an ST cut. Okay, remember yesterday we had something called an ST vertex cut, which is really similar terminology, unfortunately. But so you should know the difference. You should make sure you know the difference between a cut and a vertex cut. So an ST cut is a partitioning UW of the vertex set such that S is in U and T is in W. Okay, so it's just any way of splitting the vertices so long as S is on one side and T is on the other side. And the capacity of the cut UW, so we're going to write, for notation, we're going to write C of UW, and that's just going to be the sum of the capacities of the edges going across the cut. So sum over all arcs A from U to W. So I mean, it has, so this is U, this is W. We're looking at arcs like this that start in U and finish in W of the capacity of the arc. Okay, so you should think of this as sort of, this is the, basically if you know that from this side to this side, you have only a certain capacity between these things. Basically, what the idea is, you're not going to be able to push more than that capacity from this side to this side, because you should think of these edges as being a sort of bottleneck. Yeah. Not for this. Yeah, not for this. The thing is, nobody's forcing you to send any flow this way. Yeah. So you have some capacity on edges going this way, but you'll see that's not going to factor into it, because in some sense you want to get a lot of, say, cars from this side to this side, because this is where S is and this is where T is. If you want to get them from this side to this side, you don't really care that there's a massive road going this way, because it's not going to help you get things from this side to this, from U to W. So a massive road going from W to V, or W to U, it's not going to help you. And it's not going to hurt you either. Okay. So you shouldn't subtract it, because that would be suggesting that this big road going the wrong direction is going to harm you. Hopefully it'll be clear what I mean eventually. But that's a really good question. Okay. So here's the Max-Flow Min-Cut Theorem. Max-Flow Min-Cut. So the setup is, as we've been talking about, so D is a digraph, or a multi-digraph, C is a capacity function, so on and so forth. So under these conditions, the max flow, so the max value of F, overall F, so F is a flow, a flow from S to T, subject to C. Okay. Again, not the most elegant way of doing this, but hopefully it's clear. And this is equal to the minimum C of UW overall UW, which is an ST cut. Okay. So basically, again, the only thing that stops you from having a big flow is a small kind of bottleneck, where the bottleneck means like you have, from this side of the network to this side, you simply don't have enough capacity to push more flow across. Okay. Okay. Maybe I'll start the proof here. No, maybe I'll start the proof over there. I think this will work. Any questions about this? So, as it turns out, so this is the case actually with. So there's a lot of theorems that are going to come up in this module, which are like the max of something equals the min of something else. Right? We've already seen that with Koenig's theorem. The max size of a matching was equal to the minimum size of a vertex cover. And as it turns out, all of these things essentially all the ones we're going to see here, they all come from, at the base of them, they all sort of come from this strong duality for linear programs. Okay? So we're not going to actually use duality to prove this, but you can do that. And there's an exercise about it. So yeah. So all of these min-max theorems are always connected to, in some sense, to linear programming. Okay, but let's prove this now. So okay, so first I'm going to prove the easy direction. So but it's important to sort of be careful how you prove this, right? It's not. It's sort of. So when I write this, right, if you look back to the theorem, I want to prove the left-hand side is at most the right-hand side. So it's, this Kirchhoff's condition is important here. And so this demonstrates how you use this condition. Okay, so we want to prove the max flow is at most the min cut. That's the same as proving for every flow, the value of F is at most the value of the capacity of every cut. So we just let F be a flow. Of course, a flow which is subject to C, and UW be a cut, an ST cut. Right, and now we just do a bit of algebra. So what is the value of F? Well, it's the sum over all arcs A out of S, F of A, right? Just by definition. Now, one kind of very useful thing when you're doing any sort of algebra, surprisingly, it's really useful to add 0 to something. Right? So I'm going to add 0 a lot of times. So of course, the value is this, but obviously if I add 0 to it, I don't change anything. So here I'm summing over all V, which is in U minus S, and I just write 0. It's no problem to add 0 a lot of times. But then I can change the 0 into something else. So the first term, the first sum is the same as before. And here I'm going to sum over all V and U minus S again. And a nice way of writing 0 is to use this Kirchhoff's law. So if I sum over all the arcs A out of V, I take F of A. And I can subtract the sum of F of A over arcs into V. Now I'm realizing I did slightly mess something up. It technically doesn't matter, but I did slightly mess something up. So, okay, correction. So the value of F is actually the sum over A out of S, F of A, and this time I should have subtracted. So this is the arcs A into S, F of A. So I messed up that definition. Sorry about that. But okay, so now I need to fix this a little bit. So here you should have, this minus, so sorry about this. This is arcs A into S, f of A, right? So I mean this minus this plus 0. Okay. And the same thing here. Okay, I know this is ugly, but basically when I wrote, basically substitute this in where I wrote this. Right? Sorry about that. Okay, so now that we've got the correct thing there, let's continue this calculation. Okay, so we're starting from here, right? I can now rewrite this as, this is just the same as this, except it's for the vertex S, not for something not equal to S. So this is actually, if I put these things together, this is sum over all V and U, sum over all arcs A out of V, f of A, minus sum over all arcs A into V, f of A, right? Okay. Now it's useful to have a picture to see what's going to happen. So remember, U is this, we have U and V. They split the vertices in half, right? Now what happens, so if I look at an arc that lies completely inside, yeah? In this calculation so far. So the value of F is it's not going to matter because the flow coming out of S is going to always be the same as the flow coming into T. So in some sense, so I could have done this whole thing from the perspective of T if I wanted to, but I'm, yeah.
What it means is, as far as I know,
Yeah.
we're not going into track value, that should be going out the entire function going into T. You get an extra byte.
Well, T is not involved here at all because T is not in U. So, yeah. So U, W is a partition. U is in W. T is S is in U. T is in W. And it's a partition, so they're disjoint, right? So it splits the graph. Yeah. So T is not appearing here anywhere. Yeah. Oh, sorry, this is W. Yeah. Okay, so here's the picture, right? Now, basically you have kind of, in this sum, there's two different types of arcs that appear. Okay, in the whole digraph, there's sort of three types of arcs. Well, four, perhaps. Right? There's arcs that are completely inside of U. There's arcs that are completely inside of W. There's arcs going this way, and there's arcs going that way. But if you think about it, this one, so an arc like this is not appearing in this sum anywhere because, well, it doesn't go out or into any vertex of U. An arc like this, which is inside of U, appears twice, right? It appears once when you sum it, when you take, when you're summing the values coming out of this vertex, and it appears once when you're summing the values into this vertex. So it appears once with a plus and once with a minus. So those ones cancel out. An arc going this way appears once with a plus because it comes out of a vertex here, but it doesn't go into a vertex in U. This one appears once with a minus. So this is going to be equal to the sum of, so maybe I'll, so if you kind of go through that picture and look at what things cancel and what things don't get counted, what you end up with is that, so this is continuing from that expression at the top on the right. So this is going to be equal to sum over arcs A from U to W, f of A, minus sum over arcs A from W to U, f of A. And these are all non-negative numbers. So this is certainly at most, if you just take this sum, and because this is a valid flow, or flow subject to C, this is going to be at most the sum over all A from U to W, C of A. Okay, so this proves one direction. And this is the capacity of UW. So this is sort of the it's supposed to be the easy direction. I mean, it does take perhaps a bit of thinking to see how you can use this flow in equals flow out condition to actually do this rigorously, but it works out. So now we want to prove the other direction. So now we want basically max flow at least min cut, because we've already done the other direction. Okay? And I'm going to sort of break this, in some sense I'm going to break it into a bunch of cases, although these cases are not disjoint. So we're going to look at different types of capacity functions, but only one of the cases is going to take any work. The other ones are going to all follow as corollaries. So case 1 is that just all the arcs have capacity 1. Okay. Case 2. So I'm just going to describe the cases. The first case is going to be the only. It turns out this is the only one that matters in some sense. It's the only one that's going to take any work, but I do need to explain at least something about all of them. So the second one is that the capacity is a positive integer for all A and A. Of course, this case includes the first case, but yeah, so these aren't disjoint cases, but anyway, okay, I'll leave some room to explain it. Case 3 is that all the capacities are rational, positive rationals, okay? And the fourth case is the general case. So these are just positive reals. So does anyone, okay, maybe people won't want to answer, but does anyone see how, if you knew case 1, how you could prove case 2? So this is where the fact that we're dealing with multi-digraph, yeah, exactly, yeah. So here we would just replace each arc by CA arcs of capacity 1. And it's not hard to see that this is really the same problem. So if you had an arc which has capacity 3, I would just do 3 arcs between those vertices, all of capacity 1. Okay. Sorry, the picture's a bit small. Yeah. This is where it's kind of useful that we're dealing with multi-digraphs. Anyone see how you do this one, given case 2? So rational numbers and integers aren't really much different, right? If I have rational numbers on every arc, I can just multiply all the arcs, all the capacities by some carefully chosen number. So multiply all capacities by m, which is going to be the least common multiple of the denominators of the capacities. Right? All of these capacities are rational, so they all have a numerator and denominator. If we multiply them all by something which will clear all the denominators, then you're going to get integer valued things. So now we just apply case 2 and divide the answer by m. Right? So that's going to work. And now if you have real valued capacities, the point here is now any real number can be approximated by rational numbers. So let Cn be a capacity function where these things are rational. And the difference between Cn and C is at most, let's say, 1 over n for all arcs. Okay. Maybe if you ask me after, it's better because I've got 10 minutes. But I think I'll probably be able. But anyway, let's be safe and make sure I can get through the proof. Okay, so you can approximate reals by rationals, and if you take limits, you'll see that apply case 3 to Cn, take limits as n goes to infinity, and you'll get the result. Okay, so perhaps I won't do all the details there, but that's kind of standard. So the only thing left is case 1, where all the capacities are just 1. And now we're going to apply what we did yesterday. we're going to apply Menger's theorem. So this is for case 1. This is also basically case 1 is the same as something in the notes, which is written as corollary 4.1b. Okay, so yeah, so this proof you can find in the proof of corollary 4.1b. Okay, so right. So what is a min-cut in this case? Right, all the capacities are 1, so a min-cut is just the minimum number of arcs between U and W over all ways of partitioning the graph where S is in U, T is in W. So min-cut is just the number of arcs from U to W over all ST cuts. Right? Okay. So suppose that the so when I say min cut, I mean minimum capacity of a cut is, let's say, k for some integer k. Because it's always going to be an integer, right? Because it's just counting arcs that go between U and W. So we want to find k arc disjoint paths S to T, okay? And if you can find those k arc disjoint paths, so then we set f of a equal to 1 for all arcs A in these paths. Okay, and it's not hard to see that Kirchhoff's condition is going to hold, because whenever you have a path, one arc goes into the vertex, one arc goes out. So you have one, flow 1 going in, flow 1 going out, and they kind of match up. So remember, arc disjoint, right? These are paths that never use the same arc twice. Like, no two paths use the same arc. Okay. So the proof is, it is a kind of simple application of Menger's theorem. It's a bit hard to visualize. So we define, but yeah. You're not really responsible for knowing this proof deeply, but yeah. So define L to be a digraph. This is also kind of notationally a bit weird, because this is going to be a digraph with vertex set A. Remember, A is the arc set of D. So we're going to think, so you think of each arc of D. Now think of it as a vertex, not as an arc, okay? Where the arc, let's say A prime, is in L if the second vertex of A is the first vertex of A prime, where you think of A and A prime as being the actual arcs in D, right? So basically, you make them, so if you have the arc A, so this is in D, you have something like this, or something like this. So the second vertex of A is the first vertex of A prime. Then in L, you join A to A prime. This might be a bit weird to visualize, but this certainly will give you a digraph. Now we apply, I think it's Menger's theorem 1. Menger's theorem 2. Sorry. So Menger's theorem 2 is for finding paths between sets of vertices where, so S is going to be the arcs out of S, little s. T is the arcs out of T. So these are both vertex sets within L, right? Because arcs of D are vertices of L, okay? And, okay, actually. Yeah, so it's very possible that between today and yesterday, you may have forgotten the statement of Menger's theorem 2, but I don't have time to go through it again. But if you look into your notes, hopefully it's there. Right, so what it tells us is that either there exists k vertex disjoint paths from capital S to capital T in L. Right, so we're applying Menger's theorem to inside of L. And, well, if this was the case, so it perhaps takes a little bit of thinking, but so if this is the case, basically, so you take the vertices of this path. So the vertices of this path in L correspond to arcs of D, right? Because vertices of L are arcs of D. So the arcs in D corresponding to the vertices of these paths, well, maybe I'll just say the corresponding arcs in D. Okay, technically speaking, they're not quite going to give you arc disjoint paths, but you can, so if you take things minimal, so I don't have time to explain this, but it's not a terribly important point, but so you can, well, they do give you, if you do it correctly, arc disjoint paths S to T in D. Okay, so we assume that this isn't the case, because if it was, we would be done. So we assume that, or there exists, well, a set of vertices in L which separates S from T. So, well, okay, I'll write it like this: C subset of D at L. And probably it's time to go. Okay, maybe I'll just say it in words. I mean, so this is in the notes if you want to look at it. But basically, so Menger's theorem will give us a cut. It's a vertex cut, which is small, has at most k-1 elements. If you translate that back to D, that gives you k arcs, which separate S from T, and you can use that to get this small ST cut, which we assumed didn't exist, right? We assumed that there wasn't such a thing, because the min cut was size k, and this will give us a cut of size k-1. Okay, that's all for today. Thanks.